We're continuing our discussion of how to make Muppet models more efficient. In particular, we're talking now about how to speed up the transformer architecture for generation. And we're going to be talking about a specific technique called KV caching. And so if you remember from the transformer architecture, there is a key value lookup. And if we cache these values, you can speed up inference in Muppet models by avoiding redundant computation. But there's always a trade-off. Here we're going to spend extra memory to get faster generation. And so you can go from around 40 seconds of generation to 9 seconds of generation, about 5 times faster. And this grows as you generate more tokens. Let's refresh our memory about how transformers generate tokens. And so remember, the whole point of the transformer architecture is that you have context-specific representations for every token. And in decoding, the last token's logits predict the next token. And so you only need to figure out what is the representation of the most recent token to continue, since everything else, if you're doing mass decoding, is already fixed. It only depends on the stuff before it. But the whole point is, for a transformer, the representation is context-specific. Your final token depends on all of the previous tokens and all of the layers that go into all of the previous tokens. This isn't just like an HMM where you can take one step back. It isn't an RNN where you can just go one step back and look at one hidden layer. Here you have all of the previous tokens and all of their layers across all of the transformer heads. The mechanism by which you determine the final word's representation is through attention. So if you have some input like k-means is used for, you compute all of the hidden states for those tokens. And then each of those words will generate the following word. But once you generate a new token, like clustering by sampling, doing argmax, however you do your decoding, generating that token needed to look at all the key value pairs to figure out what it attends to in generating clustering. And so let's see if we can speed that up. So let's recall the equation for attention. We are going to have a query that comes in. We're going to have it line up against a bunch of keys, and then that will give us a pattern to weight over our V's to generate an output. So let's think about what happens for our new final token. This last token's query vector Q interacts with all of the key vectors that came before it. And so the idea here is, let's not recompute K and V for all of the previous tokens. Let's cache that across all of the layers, all of the heads. This should remind you of the sort of thing that we did with dynamic programming for other models. You save what you need to do the next step of the computation, but this is a whole lot more complicated than just remembering one vector that keeps track of what is the probability to get to this part of speech at token t-1 for the HMM. We could just cache the K matrix for all of our previous tokens across all of the layers. Once we get that, we can take our new query Q that comes in, multiply it, do the softmax, and then take the output and use that to get a new representation from V. All we have to do is just maintain a cache for each K and each V for every token. We'll need to compute that for the first time for each token, percolating up through the previous layers, but once we've computed it for the first time, we don't recompute it thereafter. And so as we do future generations in this model, we don't go through the same process of doing an entire forward pass. We cache many of these computations for the K and the V's. So this is how we built up the cache. Let's now see it in action. So here we have k-means is used for, and now we need to generate a new token following clustering. So we generate the query vector for clustering. We can then compute a new k value for clustering and a new v value for clustering. We append that to the key cache and the value cache that we had before. And so then we now have this big matrix of key values and value vectors. Our new Q comes in. We compute QK, take the softmax of that, multiply by V to get our new representation for this token. So now that we have the softmax, we can then multiply that by the cached value vectors to get our new representation for this token that goes on to the next stage. And so this cache happens at every layer as you go through your model. But as I said, you're trading off memory. You're blowing up your memory to get a faster compute. The bigger your model, the bigger your cache needs to be. For example, Llama 70 billion uses about 2.5 megabytes per token. And that's a lot. Because like you could have thousands of tokens in a relatively normal generation. And so once you get to 4K tokens, that's 10 gigabytes. You can't do this forever, so you need to be pragmatic in how you actually handle your caching. And so there are various things you could do. You could combine this with quantization, as we talked about before. You could also prune or truncate less important tokens. If it seems like you're never attending to these sorts of tokens, well, let's just forget about these in our history and we won't cache these anymore. So to wrap up our discussion of optimization, KV caching is a way to pay a little bit of extra memory to get faster generation. It's used in a lot of servers, and if you want to do it yourself in PyTorch, it's relatively easy thanks to a lot of the caching and memoization tools that you have within PyTorch. This is a relatively generalizable technique. It's not just good for transformers. Basically, any sort of computation that you're doing over and over again, you can cache the results, save that computation. And if you're doing anything repeatedly, you should be doing caching to improve the both cost in terms of dollars, because especially if you're using APIs, you're paying for every token. But even if you're running on your own hardware, caching intermediate results can be a big boon so that you're not doing the same thing over and over again. I used a relatively new technique to generate these slides. I received a free trial to use the pro version of EdCafe to generate these slides. From Avichawa, and it generated these slides automatically. It wasn't perfect. I had to do a lot of manual editing, but I was able to throw it into Google Slides relatively easily. It sped up the process. I wish that it had a Beamer output. It also has some magic words that it can't generate. For example, I tried to make slides around BPE tokenization, and it could not generate the special character to mark the end of a tokenization example. These sorts of things crop up when you're using AI to talk about AI sometimes, but it was a useful tool, and you might want to check it out. Thanks for watching this video. I picked out another video that you could watch up here. If you want to get more context for the videos, check out this link or the link in the description. It gives you readings, programming assignments, and other things that might be more helpful. Finally, help me out and help other people find this content by providing a big gradient to the recommendation algorithm. Like the video, subscribe, or leave a comment down below with mistakes that I've made, newer research that has come out, or just tell me about where you are in your journey.